Okay, think we should get started. Can all of you hear me fine? Yeah? Okay. And how many of you were in the morning session? There's a bit of overlap, so I want to avoid that. Okay, a lot of you were. Um, okay, so the idea here is to present things we've done in the last 1 year and answer any specific question you may have on any of these. A lot of these are open source, which is why I think they're interesting to talk about because you can actually look at the code or work with these without issues. They're not anything Yahoo specific. And just to introduce myself, my name is Sumit Singh and I'm a Senior Director of Products. I lead products for cloud and big data platforms at Yahoo. So what we're going to do is give you a brief overview of what the platform at Yahoo looks like because it's an old platform. We'll touch upon just very briefly on the infrastructure itself, which is an important component of the platform, some metrics, and then get into these recent work we've done, particularly Caffe on Spark for distributed deep learning, which we think is really interesting. It was open sourced last month. And then talk a little bit about how we see compute evolving at Yahoo, and then data sketches, which was another framework we open sourced a few months ago. And then we'll talk a little bit about HBase and Omid. Omid was just accepted as an Apache incubator last month. I think the code still lives on Git, but the project infrastructure is set up. So if you go to Apache, you will find it. And then Uzi was something I didn't talk in the morning, but it's a really important component as far as our platform is concerned. And I'll tell you the reason why. And then we did a set of changes which we call as ease of use or UI related work. A lot of these UIs are custom UIs. But at least you will be able to relate to what I'm talking about. They're not available in open source and there's no purpose for these to be in open source because they're very Yahoo specific. And then I'll try and leave enough time at the end for you to ask questions, anything about Yahoo or Hadoop or whatever you wish. So we, as I said, we're an old platform. We've been doing this about 10 years. And then platform for us has gradually evolved into something which I can confidently say that most of our business relies on one form or the other on the infrastructure as it has grown to where it is today. The node count is not important. A lot of people sort of think that it's an important metric, but it's not. What these nodes do is what's important. So as you can see, things go up and down from a node count standpoint over the years. One thing is consistent, though, that the HDFS storage space is constantly growing, which really tells that the volume of data you're processing for the same business continues to grow. So it doesn't mean that your revenue is growing or anything like that, but at least the amount of data you're processing for the same work, that's growing. And that's forcing the linear sort of growth in HDFS space, irrespective of the node count. Okay. There are many ways to run big data platforms. I've shown some here. You could run these as private dedicated clusters where you have one large monolithic application running on the cluster or a demanding application running on the cluster. You could set up these clusters as multi-tenant systems where search, advertising, all kinds of use cases can live on the same cluster. Hadoop handles it really well. The multi-tenancy security aspects that comes with multi-tenancy. And then as far as public cloud is concerned, I think there is also a good evolution of two different models where you can take a compute infrastructure on public cloud and spin Hadoop and other things on it. So the instances that you spin becomes a cluster for you for the time you use it. And there is also a growing sort of, I would say, breed of vendors, for the lack of a better word, who are offering purpose-built big data clusters. Databricks is a good example. VertiCloud, one of our former CTO who formed that company, that's a good example of specialized big data offerings in public cloud. Right, so we follow the hosted multi-tenant model in a private infrastructure, so our private cloud. And that's how we have been for almost all our cloud services, including Hadoop. And as I said, that works really well from a cost perspective, as well as efficiency and speed perspective. Okay. This is exactly what our stack looks like today. And if you think about the jobs, particularly the batch jobs where most of the volume is, Pig and Hive are the most popular tools at Yahoo. In fact, about 50% of all the jobs comes from Pig, and good amount comes from Hive. But the other interesting thing to note is that almost all of these jobs are orchestrated through Oozie, because in production, nobody runs jobs by hand, irrespective of the type of job. So it's all automated through Oozie. And I would go to the extent of saying that about 75% of all these jobs are coming from Oozie. They're coded with Oozie. So that's our workflow scheduler. We have UI for development, testing, and other types of purposes. We use Yahooo for that. Really large user base on Yahooo, like 2,000 individual users, 1,500 individual users use Yahooo. GDM and BigML are two sort of somewhat proprietary solutions. GDM is for data lifecycle management. Open source equivalents would be Apache Falcon. And then BigML is sort of a new initiative we have. It's all of 2 years old, and bits and pieces of it are coming out in open source, like Caffe on Spark. But vast majority of that is still sort of internal. And then all our clusters are capable of running multiple types of compute engines. The popular ones are MapReduce, of course, which is slowly shifting. That workload is slowly shifting over to Tez. So we see Tez as a really good sort of replacement for MapReduce when it comes to both Pig and Hive. And there are lots of good reasons for it, and one being utilization or cluster efficiency. It's far better with Tez than with MapReduce. And Spark is also really important for us from an iterative workload standpoint or machine learning type, model building type applications. They have successfully used Spark. By the way, all of this runs through Yarn. So Yarn is our resource manager for the last 5-6 years. We have had great success with it. And then we've always used Capacity Scheduler. Although you're totally free to use Fair Scheduler, they're converging, they're becoming very similar. Okay? Storm is a separate infrastructure for us for real-time processing, and has been like that since 2011. And then on the storage and messaging side, again, vast majority of data, all of companies' data lives on these HDFS clusters. There is some use of HBase, but it complements both Storm as well as Hadoop. So it's kind of a common link between our real-time processing and batch processing. And then HCatalog is our metastore, and the reason why we use HCatalog is because we have a lot of Pig users as well as Hive users, and we want data interoperability without worrying about the format the data is stored in. And then, of course, there is Kafka. There's really good use of Kafka for queuing type use cases or PubSub. And CMS, Cloud Messaging System, is a very similar solution than Kafka, which we have always used, but that's not open source. And then all the data from our globally distributed web servers, data centers, all come through a system called Data Highway, which is very similar to Scribe from Facebook or Flume, but that's not open source either. Most of our tools are internal, as I said. There's not a lot of sense for open sourcing that. But most of these tools are for customer onboarding onto the platform, monitoring the platform, or conducting reporting on top of the platform through systems log or log warehouses we've created for Hadoop logs, essentially. It's huge, but it's also very valuable. Okay? If you have a burning question, just raise your hand. I may be better to answer it along the way, or we can wait till the end. So in terms of our philosophy of which technology to pick and deploy at scale, we are relatively conservative because our experience tells us that it takes time to mature these things, to really make it solid for production use. So as long as the current stack meets our needs, we'll live with it. But if there's a compelling use case for which we have to introduce a new service, we go invest time in that. So as you can see, we're standardized on Yarn, we're standardized on HDFS, we're standardized on a set of JDK as well as the operating system, and a set of standardized sort of Apache components that we have picked and sort of deployed for use, but a lot of things that always stay in flight. And as need rise, we sort of push that into production at scale. But that's a good philosophy to follow. Otherwise, it can be pretty disruptive. Or you're just going to have like, I don't know, 200-person team to manage all that, which is equally disruptive. The infrastructure actually is quite simple. As I said, most of our capital is deployed in 3 separate infrastructure, and the good reasons to do that. So batch infrastructure is separate. All the Hadoop ecosystem components run there. HBase infrastructure is an isolated deployment, and we wanted it that way to give guarantees to our customers, because if you run compute on the same sort of infrastructure, then it becomes difficult to guarantee those really tight SLAs as far as HBase is concerned, either for latency or throughput reasons. And then Storm also is a separate infrastructure. So the 3 large capital deployments, about 16 Hadoop clusters, roughly 13 HBase clusters, and roughly 13 Storm clusters, distributed across multiple data centers in the United States. The good thing, though, is that these 3 infrastructure, while they're deployed separately as clusters, there's no real distinction between, let's say, a Hadoop server and an HBase server, because they all sit on a common network backplane, and the backplane is really large. It has enough capacity to support, as I said, about 20,000 plus servers in a single data center. So whether you're going from one rack to the other in a Hadoop cluster, or from that rack into an HBase cluster or Storm cluster, they're more or less the same thing, which is why an isolated deployment makes sense if you have a common network backplane. Okay? I talked about it this morning. This is a project which we started to make space in one of our data centers. So these are 3 of our research clusters, non-production clusters. We had to retire them because they were A, old, and B, we needed to make space. So we were very successfully able to migrate about 100 active projects from these clusters onto a new cluster, and this is our largest cluster today. And just by modernizing that hardware, we were able to retire 10, 11,000 servers in favor of 2,200 modern servers. But the good thing here is that the amount of total cost of ownership we were able to bring down by this consolidation was really phenomenal. And it basically funded all the money we spent on setting up this cluster. So the morale here is that keeping an eye on your total cost of ownership is exceptionally important as you scale your big data infrastructure. And we track that per tenant, we track that per cluster, and we track that for the overall platform really carefully. For each of the resource type we offer to our customers, as well as the utilization, which is extremely important. If you set up large infrastructure which is underutilized, you will waste a lot of money. So keeping average utilization above 70%, I think, is a core goal, but it's really hard because almost all the time during the day, your clusters are hitting 100%. They're totally full. So if someone launches a job, it just waits, sits there. So you have to manage that expectation, but we think there is still room for improvement through really cleverly designed features and tooling to push the utilization boundaries further. I talked about it this morning. I'm going to skip this. But the interesting thing that happened with this research cluster is that we were able to set up newer forms of hardware, newer forms of networking, and just experiment with that and see where it goes. So we basically designed some really dense GPU servers with a vendor for deep learning applications. We have a lot of images from Flickr, a lot of video properties, so deep learning is a critical demand or application that we need to satisfy. And we always thought that since all the data is on this singular infrastructure, why not conduct machine learning on the same infrastructure where the data is? Which was the motivation for setting things up this way. But the 10 gig networking we have between our servers and top of rack and then into the backplane, we thought that was not enough to handle deep learning type applications. So what we did was we connected these GPU servers together with 100 gig InfiniBand just as an alternate path, and that had two benefits. It gives you RDMA for direct memory access into these GPU servers. And the other thing it does is that it doesn't saturate our top-of-rack switches for these types of applications. And then server-to-server communication makes you scale these deep learning applications easily. And then we also set up high memory servers, as you see, for a special purpose application, which we call parameter server, which basically coordinates training parameters for large-scale machine learning applications. So again, if you're not familiar with these features, I think they're worthwhile looking at. So Yarn has a new feature called node label, which is what we were able to use to target specific applications to specific types of hardware, all living in the same cluster, same rack. And so node label is really interesting and simple. It's an administrative feature where you label certain nodes as XYZ. And what it lets you do is that through the capacity scheduler queues, you can target applications to go to certain labels. So if you label all your GPU servers as X, and the deep learning applications come in, you can send them to GPU servers instead of everywhere else in the same cluster. So you can set up really heterogeneous clusters and use this feature to target applications to specific types of hardware. This is an evolving feature. We started using it in its very early days, but I hope it evolves further. So that gave rise to this effort, which we call as Caffe on Spark. Caffe is a very popular framework, if you're not familiar with it, for deep learning. And then Spark, of course, is a popular framework for model building. So what we were able to do is put the two together in a way that was sort of advantageous for us or met the needs we had when we began the project. One of the objectives we had was not to set up a specialized cluster for deep learning, because all the data was sitting on these Hadoop clusters, and had we done that, then you would keep moving data back, and so data back and forth, models back and forth, and that was not desirable because A, it's slow and painful. So that was one requirement we had. The other requirement we had was that just to use the existing infrastructure that we have and only put in things that we would need on top. Because all the Flickr images and other things were already sitting on Hadoop clusters for tagging. So it made sense to actually do it right there. and that's the sort of setup here. The other thing that was required was that, let's say you did deep learning and you came up with your model, you saved it somewhere, but that you want to run further algorithms on it, let's say logistic regression afterwards. How can you do that in sort of single steps or streamlined steps? So that was also important, which is why we actually went with Spark here, so it's basically is launched as a Spark application. The Caffe is launched as a Spark application with some really good advantages. So let's get into that. But before we do that, so these are the applications we talked about, weather, pulling in sort of relevant pictures based on the temperature conditions or local conditions, requires that intelligence. Flickr, as I said, facial recognition is one use case for deep learning, where most of the people who upload these pictures will never say that he's this person, and you need to detect that. So deep learning is really good for that. This is scene detection, another good use case. We have lots of other use cases just within Flickr, like beauty detection. These pictures are deemed beautiful by the algorithm. Tagging is a good use case. This is elephant, this is cat, this is mouse. The machine recognizes that. And after a while, it becomes really good at predicting what it is. So architecture was very simple. As I said, all our data sets resided in HDFS. So HDFS, it became the source of data for Caffe on Spark. All of it was launched as Spark executors. The Caffe itself was launched as Spark executors with few enhancements, and one of the primary enhancements was that the executors could talk to each other, which is why we connected these GPU servers together with InfiniBand so that you can do an MPI style exchange, be it over TCP or Ethernet or InfiniBand. So that communication was important for scale. And then you could put the output the model back on HDFS again, and then run MLlib or other things on top, like or we have a homegrown solution for logistic regression, so you run logistic regression on top of that. So this slide just highlights that incremental learning aspect of it. Like, so you did deep learning, and then you did your, let's say, classification or other things afterwards, all in a sort of seamless sequence of steps, without really leaving the cluster or the data leaving the cluster or you doing anything more special purpose. And all of it can be launched with a single API. It's a single command. So it's really easy to conduct deep learning with this framework. And I think I touched upon most of these benefits. One thing I also wanted to touch upon is that, let's say you don't have budget to buy GPU servers, they're expensive. So you could also launch Caffe on Spark and on Amazon EC2 instances. So they offer GPU instances. We have tried it out. In fact, the GitHub repo actually talks about steps you can take to test or try Caffe on Spark on AWS. It's really easy. And I actually encourage you, if you have a need like that, application like that, try it out. Okay, any questions so far? I have plenty of time, 20 minutes left, yeah.
So it seems, are you using any data flows engines between your deep learning and machine learning, for example, applications?
Data flow engine.
So for example, how you organize scheduling the task between, if you have something to do on deep learning, and then you want to further schedule it on machine learning.
It's just a sequence of Spark jobs. Yeah.
Just manually define the kind of any.
There's a config file. Yeah. Okay, let's keep going. So I talked about compute. So these are the sources of compute, and I think I've described this in detail. A set of compute comes from our data management task, the GDM that I talked about. This literally copies data back and forth between clusters, from non-cluster sources over to Hadoop clusters. Believe me or not, we still use Java MapReduce APIs in production. These were coded like many, many years ago. They still run. Pig, though, is the most popular source of compute for us, Pig scripts. And then Hive also, and then the machine learning applications or algorithms. So these are the sources of compute, batch compute. And then they could choose any of these compute engines, MapReduce or Tez or Spark. What we're doing today is that we're transparently migrating all the Pig jobs and Hive jobs over to Tez. Many have already done. So the default compute engine for Pig and Hive has now been switched over to Tez. But there are people who still go back and stick to MapReduce. They would actually do set execution engine MapReduce, MR. I don't know why, they just don't feel comfortable with Tez. So it's going to take time, and it is taking time. It's just not happening as fast as we had hoped to take away MapReduce because of its inefficiencies and replace it with Tez. But we're doing that. And then all of that runs on Yarn. So Yarn, as I said, works really fine for us from both scheduling standpoint and resource management standpoint. And all the data is, of course, on HDFS. There is some use of Slider also if there's a project on which you could build custom Yarn applications. So all our machine learning applications run on top of Slider as Yarn applications. This is the sort of proof that your job volume is growing because your data is growing, whether your use cases are growing or not. And we're growing at a very rapid pace. So we're now like looking at 1.3, 1.4 million jobs a day, and they're just growing. So a lot of people who were not doing or building applications on top of the infrastructure are doing so. And then the amount of data they're dealing with is also increasing very rapidly. But this is happening with compute. What's happening with compute? This is real. This is what it is. We hoped this had gone to 0, but it, as I said, will take forever. Hopefully, in next quarter or two, we have a good goal to sort of get it down to 20%, and we'll see how that goes. And then for real-time compute or event-based processing, yeah.
On the last slide, there was a period of massive drop in MapReduce, a big spike.
This one?
Yeah.
Yeah.
What happened there?
Oh, people testing. Large-scale pipelines, changing over to Tez, letting their pipeline run for some time, and then switching back to MapReduce. Really simple to explain. Good question. Some large user turned over to test their pipelines that it runs successfully in Tez and switched back to MapReduce. It will take time. And by the way, there are issues too, right? So it's a new execution engine, and we're fixing things as we discover them. There's a lot of code. It utilizes a lot of MapReduce code, but still a lot of new code. And it's very sophisticated in how it optimizes for both speed and utilization, like cluster resources, as well as guaranteeing you consistent performance. A lot of optimizations within Tez. Yeah.
How do you expect LLAP to kind of factor into this?
Yeah. Good question. So LLAP runs as a separate daemon on each data node. Do you guys all understand what he's asking?
No.
Okay, so LLAP is a daemon proposed for Hive queries to bring the query processing time even further down. So Tez has done a lot, and then you bring it down further by caching data. So to cache data effectively in a fault-tolerant fashion, LLAP is the proposed daemon that would do that. So today, I think and it's generic, like you could do it in different ways, but right now the proposal and the work is really being done for Hive. The way we think about it is that we might set up separate queues for extreme latency sensitive applications, and just that queue launches LLAP daemons or node labels or something to just target the extreme latency sensitive queries, go into that queue. And then we don't run LLAP daemon across the cluster. We only run it on specific servers in the cluster. But the people who want to use that, just like deep learning applications. We don't want to open up GPU queue for everybody because GPU resources are expensive. So only people who truly need it go there. And it's easy, as I said, to target applications to specific hardware or specific frameworks when you run clusters with extreme heterogeneity. It's totally possible. That's the current thinking. We haven't rolled it out in production yet. Yeah.
I have a question. Which distribution of Hadoop you are using?
Oh, we build our own. I don't know. We release like twice a day.
Well, twice a day and you're going directly to production.
Yeah. Well, okay. So there's a philosophy we follow. We have 3 grades of clusters. Vast majority of the clusters are production clusters, and a couple of clusters, really small, we call them sandbox. And then a set of clusters we call research clusters. And the path of deployment is from sandbox to research to production. A lot of problems are discovered when we roll it out. So we have CI/CD across all our clusters, but the CI/CD without interruption hits the sandbox cluster. The sandbox cluster uncovers a lot of problems. Then we go back, fix, roll out again, see if it works. If it works there, move it to research clusters. Research clusters has actual workloads running at scale that uncovers even more problems. Think of it as like peeling the onion and until you get to the core. So really revenue sensitive production clusters are the last ones to get upgraded, with the hope that you've caught all the bugs and issues beforehand. So the rollouts follow a schedule, and we know what that schedule is, but it can happen very quickly. Things like Pig and others, we can push it out across all 16, 20 clusters in a single day because it's more or less a client-side concept. Hive has some, but that can also be quite fast. Anything that doesn't have a server-side dependency can be very quick. The server-side changes take time. We're more cautious on those changes. Major releases happen infrequently. Minor patches go in all the time.
And what's the process of your upgrade? Are you bringing the cluster offline, or you're trying to do it in the rolling mode?
No.
I'm talking about the major upgrade.
Yeah.
Like
Everything follows rolling upgrades now. There is no cluster downtime at all. And all rolling upgrades are work preserving. Does that answer the question?
Yeah, but still questions. For instance, high metadata, how you're operating, you need to have a downtime for it. That's the
The
only
meta
part.
store, yeah,
Yes.
yeah.
High meta store, the only part which
Yeah.
you cannot.
Yeah, but so there are BCPs built at multiple levels. I'm going to digress real big, so we'll run out of time. Maybe we should talk later. I'll give you all the operational strategies we use to handle those things. We're able to do it well. Yeah, there are downtimes. I won't deny it, but the availability is fairly good. It's not 10 nines or 5 nines, but it's several nines, which is not bad for data infrastructure. Okay, I'm really short on time, so I'll be very fast. Storm, we run multiple tenants topologies on the same Storm cluster, and we started playing around with the scheduler. It went through evolution. We built something called as isolation scheduler. We would get a set of supervisors to specific tenants, basically dedicated machines in the same cluster. And then we kept moving on. And now we're at this incarnation of this thing called resource-aware scheduler. It was just released with Storm 1 like a few days ago. Resource-aware scheduler gives you guarantees on network, on disk, on memory. So you can actually specify the resources your topologies want to use. And that's probably the most flexible way, much like Yarn operates, way to allocate resources to topologies. Distributed cache API is very similar to the concept that is there in Hadoop, where you want to ship large files and share that among topologies. It lets you do that. Throughput is okay. Debuggability, a lot of work has gone in because debuggability was a pain with Storm. It was really hard to debug topologies while they're running, particularly in production. So a ton of features have been built just to deal with that, such as distributed search and logs, tuple sampling while things are in flight. You can dynamically profile your workers, things like that. Pacemaker server is sort of Yahoo specific. We had a project where we needed to scale the Storm clusters, and we found that Zookeeper was a bottleneck. So it's just an alternate key value store in memory that offloads Zookeeper and allows us to scale because Nimbus. Okay, well, let's ignore the details. If you guys want to talk, we can talk later. There was no good benchmark for streaming systems. In every conference, I hear people saying, okay, should I use Spark streaming? Should I use Flink? Should I use Storm? Should I use something else? So we started off with a benchmark, and we were getting the same questions. Is Storm good enough? So we put together a benchmark and then open sourced that as well. So it's on GitHub, and compared a few systems, and we found Storm to be good enough for us, so we were going to continue with that. Sketches, the concept is simple, but the details are difficult to get in such a short time. But think of queries. There are queries that are problematic. They just don't finish quickly, or that needs infinite resources for them to finish. And Sketches comes in where you can tolerate certain loss, inaccuracy of the results, or the completeness of the results, but then it can finish real fast. So it's sort of a summarization technique. Works really well for data that can be streamed. And then these sketches have a property which we call as additive or mergeable. So and that helps it parallelize the computations or summarization, which is why it's so quick. And it's a really good quality implementation, so I encourage you to look at it. It's led by a guy named Leadodes in our analytics team. Let me skip this. This just shows how count distinct works with sketches. Good thing is that it works really well with Pig, Hive, as well as Druid. We use Druid for a lot of our user-facing analytics, such as Mobile Developer Suite, which uses Flurry analytics. So, billions of mobile devices, it tracks them all real time. And Hive and Pig also works faster with sketches if you can live with the approximation. For the types of things we do, count distinct and others, if there is an error of 5 users not being counted out of 1 billion, we're totally fine. So if you have use cases like that, I think sketches help tremendously. HBase, I talked about our deployment, our security work. Let me skip those. This is region group. I have 4 or 5 minutes left. Okay, so let's talk about some of the work we've done. We split the meta table into multiple regions, or smaller meta tables, and the reason was that meta access becomes a bottleneck when you start to scale or start to host a lot of regions on the same cluster. So this is just some initial numbers from not splitting and splitting, and you can see the speed up. But it's a simple thing that you spread it across multiple region servers. So you don't have a single meta to sort of act as the bottleneck in the system. It also speeds up region assignments, by the way. This is favored nodes. So favored nodes is not a new feature. It's already there, but we sort of refactored it for groups, region server groups. The idea is very simple. You improve locality, and the reason why you want to improve locality in a group is that you want better read throughput. So better read throughput can only happen if you have good locality, as well as it also helps with network traffic. So you can again see the results much better with favored nodes. Humongous tables, I will skip that. I don't know how applicable it is for a vast majority of you, but these are gigantic tables that can take forever and start to hit lots of different types of limits. So with a sort of a hierarchical file type implementation, we've been able to overcome some of those limits. That's what this talks about. I want to talk about Omid because it's a new incubator project. So again, we have had a lot of use cases in our search systems in particular, as well as personalization systems that wanted RDBMS style transactions on top of HBase. And HBase doesn't have native support for transaction. And while it seems very simple that a transaction is a simple bundle of multiple reads and writes as one, to do that in a fault-tolerant fashion and a performant fashion is hard. And so Omid was a project started by Yahoo Labs back in 2011, and we sort of revamped that project and implemented it for our search systems. And it has worked really well. It has all kinds of facilities with it. So now we're looking at some of the important projects in the Apache ecosystem like Hive and Phoenix to adopt it, which is one of the reasons why we're moving it to Apache. So wherever you have a need for transactions or asset properties on top of things like HBase, I think Omid is a phenomenal implementation, a robust implementation to do those. And we already have it in production. We handle millions of transactions on Omid using HBase as its backend. Again, I have 2 minutes left, so let me skip these. Uzi also. How many of you use Uzi? Are you interested in knowing about Uzi 2, 3, 4? Okay, so real quick, I'll try and summarize this. So large-scale pipelines have lots of weird use cases where they want to manage dependencies between multiple stages of data processing. So we have done recent work. It's called input checks. That's the tag here, input logic. As you can see, the input logic. And this allows you to code a lot of flexible schemes to manage dependencies between various stages of data pipelines. And so what I would do is, since the slides would be posted, they're very self-explanatory. You can read these examples of how you use input check to do different types of dependency management. This is an example where you use declare certain data sets as mandatory, certain data sets as optional, and manage that very, very well. You could also specify a primary data set and a BCP data set, and if primary data set is not available, you can always read that data set from a BCP instance. In many cases, data is not guaranteed, but you still want to continue processing. You can specify that very easily. You could also set priorities among data sets. They say, read this data set first, and only when you're not happy, move then further. Or set precedents. You can combine data sets. So there are certain sources of data where you can have more than one provider, or you rely on more than one provider for the same data. You can manage all that provider with priority with Uzi, with the input check scheme. Ease of use, we have automated vast majority of our customer onboarding through portals. And these portals have the notion of project. So each tenant for us is a project. And we do all our customer collaboration on the same portal. The other basic tenet of working with such a sort of scheme with your multiple customers, with lots of customers, internal customers, is that you want to be very transparent in terms of the resources you've allocated to them, resources they are using today. They can make requests in a very automated fashion on the same portal to request increases. We have capital approval and other types of processes within the organization integrated in the same portal, as well as full cost transparency in terms of what it's costing the money, what it's costing the company, again on a cost basis to these tenants for doing certain projects. So now tenants are actually able to easily figure out whether the project is viable or not, what is the return on investment, certain projects, because all the cost is transparent to the company. And then there are a host of tools that allows them to dig deeper into how things are going, such as queue utilization, individual users within the queue who have permissions to submit jobs, and who's causing trouble, who's not causing trouble. We also have automated tools for discovering data. So with vast amount of data, it's really hard to figure things out as to where is the data. So on which cluster or which data center with data discovery tool, you can just type in the types of data set you want to look for, and it gives you the results back. It's all based off of HCatalog Metastore. Basically just reads the Metastore's schemas and uncovers that. So it does not compromise with the security or access of data, but requesting access to certain data sets is then integrated in the same portal. Let me skip the governance stuff. I know a lot of you are not interested in it. We use Hue, I told you that, don't have time to get into it. And I covered this before. Machine learning, utilization improvement, lots of users, lots of committers. We have a blog, thank you. I will be out at the Yahoo booth for another couple of hours, so if you have questions, I'm happy to. Somebody wanted to learn operational tricks, I'm happy to share those.